Analysis of zero group cation ammonium ion. First we take the ammonium salt solution. To this we add dilute NaOH. So ammonium is acidic, NaOH is base. So because of acid-base reaction, ammonia gas will evolve. And because of smell, we can identify it can be ammonia. And then we put the glass rod which is dipped in the HCl solution so that ammonia vapors combine with HCl and forms dense fumes of ammonium chloride, white dense fumes of ammonium chloride. Now we do confirmation test. For confirmation test we take ammonia solution, and to this ammonia solution we add NaOH so that ammonia gas will evolve, and to this ammonia gas we add Nestler's reagent K2HgI4. We add Nestler's reagent K2HgI4 and it forms brown PPT of HGO HgNH2I. HGO HgNH2I. It is basic nature mercury 2 amido iodine. Mercury 2 amido iodine. HgNH2I, mercury 2 amido iodine. It is a brown PPT. The formation of brown PPT confirms the presence of ammonia in the solution. After testing of ammonium ion, if ammonium ion is absent, look for the other cations. For that purpose, we have to follow this procedure. Take the original salt solution, add dilute HCl. If precipitate is formed, group 1 cations are present. If precipitate is not formed, then pass H2O to the same solution. Then observe the solution. If precipitate is formed, group 2 cations are present. If precipitate is not formed, then look for the group 3 cations. Before testing group 3 cations, take the original salt solution and then heat with conc HNO3. After some time, cool the solution, add solid ammonium chloride and ammonium hydroxide in excess. Solid ammonium chloride and ammonium hydroxide in excess. If precipitate is formed, group 3 cations are present. If precipitate is not present, then add H2S. This is the group 4 reagent along with ammonium chloride, ammonium hydroxide. And if precipitate is formed, group 4 cations are present. If group 4 cations are absent, then again take the original solution, add ammonium hydroxide and ammonium carbonate. Ammonium hydroxide and ammonium carbonate. If PPT is formed, group 5 cations are present. If PPT is formed, group 5 cations are present. If precipitate is not formed, then look for the group 6 cation magnesium. Then look for the group 6 cation magnesium by considering the original salt solution. So this is the flow chart for testing of cations present in the solution. Analysis of group 1 cations. Group 1 reagent is dilute HCl. Group 1 cations are Ag plus, Pb plus 2 and Hg2 2 plus mercurous ion. We add dilute HCl to the original salt solution. If white PPT is observed, it can be AgCl or mercurous chloride Hg2Cl2 or PbCl2. Any one of these possible. After that we boil the solution. If the PPT is soluble, then the corresponding PPT is lead chloride because lead chloride is soluble in hot water. AgCl Hg2Cl2 not soluble in hot water but PbCl2 soluble in hot water. One of the first group cation Pb plus 2, when we add first group reagent dilute HCl, it forms white PPT of PbCl2 and PbCl2 insoluble in cold water. When we boil the solution, it is soluble. So it is a soluble PbCl2, and this hot solution divided into three parts. To the first part, we are adding potassium iodide so that it forms yellow PPT of PbI2. Yellow PPT of PbI2. When we boil the solution, this PbI2 soluble in water. This PbI2 soluble in water. To the second part, we add potassium chromate. Potassium chromate. It forms yellow PPT of lead chromate. Yellow PPT of lead chromate. When we add dilute NaOH, this yellow PPT soluble in NaOH. This yellow PPT soluble in NaOH because of formation of soluble complex tetrahydroxoplumbate. Tetrahydroxoplumbate. It is a soluble complex and it is colorless. To the third part, we add dilute H2SO4 so that it forms white PPT of lead sulfate. White PPT of lead sulfate. And to the white PPT, we add ammonium acetate and small amount of acetic acid. Ammonium acetate and small amount of acetic acid. So small amount of acetic acid promotes the reaction and forms corresponding tetraaceto ammonium tetraacetoplumbate complex. Ammonium tetraacetoplumbate complex, and which is water soluble and colorless. Water soluble and colorless. Analysis of second group cations. To the second group cations, first we add group reagent H2S in the presence of HCl. In the presence of HCl, the sulfide concentration is low, therefore few cations form PPT. To the PPT, we add yellow ammonium sulfide solution. Yellow ammonium sulfide solution. So that few precipitates are insoluble, few precipitates are soluble. First we look into insoluble precipitates. This is a 2A group. If the precipitate is insoluble in ammonium sulfide, those are considered as 2A group. In the 2A group, we are having mercuric sulfide black PPT, lead sulfide black PPT, cupric sulfide black PPT, cadmium sulfide yellow PPT, bismuth sulfide black PPT. And the precipitates which are soluble in ammonium sulfide is arsenic sulfide yellow PPT As2S5, yellow PPT SNS, brown PPT SNS2, yellow PPT SB2S3, orange PPT SB2S5, orange PPT. So in the second group category, we are having 2A group cations precipitates and 2B group cation precipitates. 2A group cations are insoluble in yellow ammonium sulfide and 2B group are soluble in yellow ammonium sulfide. Analysis of second group cation mercuric, lead, copper, cadmium and bismuth. Now we discuss about the lead. To the lead ion, we add group reagent H2S and HCl. In the presence of HCl, H2S undergo slightly dissociation and small sulfide concentration combine with Pb plus 2 and forms black PPT of lead sulfide. Black PPT of lead sulfide. And this lead sulfide dissolve in HNO3. This lead sulfide dissolve in HNO3 and forms lead nitrate. Lead nitrate Pb plus 2 and NO3 minus lead nitrate. And here redox reaction takes place. Sulfide will be oxidized to sulfur. Sulfide will be oxidized to sulfur. Nitrate ion will be reduced to NO. Sulfide will be oxidized to sulfur. Nitrate ion will be reduced to NO. And to this lead nitrate solution, we add dilute H2SO4. So Pb plus 2 and SO4 minus 2 will combine and forms white PPT of lead sulfate, white PPT of lead sulfate. And this lead sulfate soluble in ammonium acetate in the presence of acetic acid. This white PPT lead sulfate soluble in ammonium acetate in the presence of acetic acid because of formation of complex ammonium tetraacetoplumbate. Ammonium tetraacetoplumbate. It is a soluble complex. Now this soluble complex divided into two parts. To the first part add Ki so that it forms LOPPT of lead iodide, LOPPT of lead iodide, and which on boiling soluble in water, which on boiling soluble in water. To the second part of the solution add potassium chromate so that it forms LOPPT of lead chromate, LOPPT of lead chromate. And this lead chromate soluble in NaOH because of formation of complex tetrahydroxoplumbate, tetrahydroxoplumbate. Like this we can identify presence of lead in the second group. Analysis of 2A group cations, mercuric, lead, cupric, cadmium, bismuth. Now we discuss about the cupric ion. To the cupric salt, we add second group reagent H2S in the presence of HCl. Because of low sulfide concentration, here cupric sulfide will form and the cupric sulfide is black PPT. This is soluble in HNO3 like lead sulfide and it forms copper nitrate solution. Copper nitrate solution. In this case, nitrate ion will be reduced to NO. Sulfur will be oxidized to, initially it converts into sulfur. Sulfide converts into sulfur and sulfur again oxidized to sulfate. And this sulfate form copper sulfate with cupric nitrate. So Cu plus 2 and SO4 minus 2. It is a blue solution. When copper sulfate present in the water, it forms a blue solution. To the blue solution, we are adding ammonia, ammonium hydroxide. It forms basic copper sulfate. It is a basic copper sulfate, CuOH2. Some amount of copper combined with OH minus, so it forms a CuOH2 and CuSO4. It is called basic copper sulfate and it is a blue PPT, blue colored PPT. If I add excess ammonia, it is soluble because of formation of complex. This basic copper sulfate PPT soluble in excess of ammonia because of formation of complex. And the complex formula is CuNH34SO4 tetraamine copper sulfate, and the color intensity is more when compared to previous one, so it is a deep blue color. To the deep blue color precipitate we add acetic acid, and here ammonia is present, so ammonia react with acid and the PPT, deep blue colored PPT, dissolves and forms blue solution of copper sulfate, blue solution of copper sulfate. To the solution we add potassium ferrocyanide, so that it forms chocolate brown PPT, of Cu2FeCN6, Cu2FeCN6. When we add potassium ferrocyanide to copper sulfate solution, Cu plus 2 combine with the anion of the complex and forms chocolate brown PPT, Cu2FeCN6. So this is how we can identify copper ion present in the solution. Analysis of 2B group cations As plus 3, As plus 5, Sn plus 2, Sn plus 4, Sp plus 3, Sp plus 5. Now we discuss about the As plus 3. To the As plus 3 salt solution, we add H2S in the presence of HCl. Because of HCl, the sulfide concentration is low, and in the low concentration of sulfide, As plus 3 combined with sulfide form LOPPT of arsenic sulfide, As2S3. As2S3, it is a LOPPT. To this we add yellow ammonium sulfide. It is a ammonium sulfide formula, ammonium sulfide. When we add yellow ammonium sulfide, this LOPPT is soluble because of formation of NH43 ASS4, NH43 ASS4, ammonium thioarsenate, ammonium thioarsenate. When we add HCl, when we add HCl, again it forms LOPPT of As2S5, As2S5. Here arsenic state is plus 5. It is also LOPPT. To this, if I add HNO3, it is soluble. To this, if I add HNO3, it is soluble and forms arsenic acid. And forms arsenic acid. To this arsenic acid, we add ammonium molybdate. In the presence of HNO3, we add ammonium molybdate and it forms LOPPT. It forms LOPPT. NH43 AS MO3O4 4 times. NH43 AS MO3O10 4 times. It is a LOPPT. It confirms the presence of As plus 3 in the original solution. Analysis of group 3 cations. Group 3 reagent ammonium chloride and ammonium hydroxide, and the group 3 cations Al plus 3, Fe plus 3 and Cr plus 3. If group 2 is absent, then take the original solution. That means after performing first group cation test, second group cation test, if both are absent, then take the original solution and add 2-3 drops of Cation O3. Add 2-3 drops of Cation O3 to oxidize Fe plus 2 to Fe plus 3. If any Fe plus 2 is there, so that should be oxidized to Fe plus 3. And then heat the solution for few minutes. And then heat the solution for few minutes. After that, cool the solution and add solid ammonium chloride and excess of ammonium hydroxide. It is a third group reagent till the solution smells ammonia. And shake the test tube after addition of ammonium chloride and ammonium hydroxide. If we observe brown, white or green, any one of these PPT, it indicates the presence of third group cations. Aluminum hydroxide, white PPT, ferric hydroxide, reddish brown PPT, chromium hydroxide, green PPT. So this is how we can at least get the basic idea whether third group cations are present or not. Now we discuss about the confirmation test of Al plus 3 and Fe plus 3, which are in our syllabus. Group 3 reagent ammonium chloride and ammonium hydroxide. Group 3 cations Al plus 3, Fe plus 3, Cr plus 3. Now we discuss about the Al plus 3. We take Al plus 3 salt solution. To the salt solution, we are adding group reagent NH4OH, NH4Cl, and to the second part we are adding NaOH. In both cases, white gelatinous PPT of aluminum hydroxide will form. Now, if I add excess of ammonia, it is insoluble. In excess of ammonia, it is insoluble. But in excess of NaOH, it is soluble because aluminum hydroxide is amphoteric. Therefore, it forms a soluble complex AlOH4 minus. If I add sodium, NaAlOH4 minus. If I add sodium ion also, the formula is NaAlOH4 minus. It decomposes to sodium meta-aluminate, NaAlO2. Sodium meta-aluminate, NaAlO2. To the sodium meta-aluminate, if I add ammonium chloride and heat, ammonium chloride is acidic, sodium meta-aluminate is basic. As a result, acid-base reaction takes place. Again, we get corresponding AlCl3 solution. We get corresponding AlCl3 solution. And to this AlCl3 solution, we are adding the blue litmus solution. To the AlCl3 solution, we are adding blue litmus solution. Because AlCl3 is acidic in nature, AlCl3 is a salt of strong acid and weak base. Strong acid and weak base. Therefore, it is the acidic solution. To the acidic solution, when we add blue litmus, it converts into red color. It converts into red color. And to the red color solution, we are adding ammonium hydroxide. Ammonium hydroxide. So again, OH minus combined with Al plus 3 and forms aluminum hydroxide. But because of addition of blue litmus, this white gelatinous PPT absorb the blue color. Therefore, the solution looks like a blue solution, but it is actually white solution of aluminum hydroxide, and the blue color of litmus adsorbed on the aluminum hydroxide, and it is insoluble adsorption complex, and it floats in the solution. Therefore it looks like a lake. Therefore it is also called lake test. Group 3 reagent, ammonium chloride, ammonium hydroxide. So here hydroxides precipitates will form, and the group 3 cations, aluminum, iron and chromium, Al plus 3, Fe plus 3, Cr plus 3. Now we discuss about the Fe plus 3. The salt solution contains Fe plus 3, salt solution. And to this salt solution, the group reagent ammonium hydroxide is added. So it forms Fe plus 3 combined with OH minus forms ferric hydroxide, reddish brown PPT. If I add excess of ammonium hydroxide, the reddish brown PPT insoluble. To the original salt solution, add excess of NaOH. When we are adding small concentration also, it is forming ferric hydroxide. That means it is a strong base. Definitely it will form reddish brown PPT, FeOH3. If I add excess of NaOH, it is also insoluble. In excess of NaOH, FeOH3 insoluble. When we add NH4OH, initially it forms ferric hydroxide red brown PPT, and if I add HCl, the ferric hydroxide is base, HCl is acid, so acid base reaction, salt will form. That means ferric hydroxide soluble in HCl. Now the FeCl3 solution divided into 3 parts, and first we are adding potassium ferrocyanide. So here we are having Fe plus 3, Fe plus 3 cation, and it is an anion having the minus 4 charge. And finally, it forms Prussian blue PPT, Fe4, FeCN6 3 times. It forms corresponding Prussian blue PPT. If I add excess of reagent, K4 FeCl6, if I add excess, it forms soluble Prussian blue. That means when we add a limited amount, it forms a PPT, but when we add excess, the PPT is soluble because of formation of Prussian blue. It is a colloidal solution. The formula is KFeFeCN6. KFeFeCN6. To the FeCl3 solution, if I add potassium thiocyanate in slightly acidic medium, SCN minus combined with Fe plus 3. SCN minus combined with Fe plus 3 and forms corresponding blood red solution. Blood red solution FeSCN 2 plus. FeSCN 2 plus. Of course, FeSCN 3 possible, FeSCN 2 plus 1 also possible. So this is a test for Fe plus 3 salt solution. Analysis of group 4 cations. Group 4 reagent is H2S and ammonium hydroxide. In the presence of base ammonium hydroxide, H2S equilibrium will be shifted to forward direction so that the sulfide concentration is little bit high and the corresponding cations form corresponding precipitates. And the group 4 cations are Zn plus 2, Mn plus 2, Ni plus 2 and CO plus 2. Once group 3 cations are absent, you can pass H2S gas into the same solution. If precipitate appears, it indicates the presence of group 4 cations. The possible precipitates are white PPT of zinc sulfide, dirty pink PPT or buff colored PPT of manganese sulfide, black PPT of nickel sulfide, black PPT of cobalt sulfide. So these are the possible precipitates that can be present. Now we identify few ions from these 4 cations. Confirmatory test for group 4 cations. First we discuss about the zinc. So first we take the original salt solution. To the original salt solution we pass H2S in the presence of ammonium hydroxide so that it forms white PPT of zinc sulfide. White PPT of zinc sulfide. And to this we add dilute HCl. So zinc sulfide dissolve in dilute HCl so that it forms soluble zinc chloride. Soluble zinc chloride. Divide this solution into two parts. To the first part, add sodium hydroxide so that Zn plus 2 combined with OH minus and forms white PPT of zinc hydroxide. To this white PPT of zinc hydroxide, add excess amount of NaOH so that OH minus combined with zinc and forms sodium zincate Na2ZnOH4 complex. On heating, it converts into sodium zincate Na2ZnO2. Na2ZnO2. This complex is water soluble. On heating, it decomposes and forms corresponding soluble Na2ZnO2. Na2ZnO2, sodium zincate. To the second part, add ammonium hydroxide and potassium ferrocyanide. Ammonium hydroxide followed by potassium ferrocyanide. So before addition of potassium ferrocyanide, we have to neutralize the solution because ZnCl2 is acidic in nature. So to neutralize the solution, we are adding ammonia. After that, we are adding potassium ferrocyanide so that it zinc combined with the this anion part of the complex and converts into another complex Zn2FeCN6. Zn2FeCN6. It is a white or bluish white PPT. It looks like white or bluish white PPT. So this is how we confirm the presence of zinc in the original salt solution. Confirmatory test for group 4 cations, and here we discuss about the manganese. First we take the original salt solution of manganese. To the solution add group reagent H2S and ammonium hydroxide so that it forms buff or dirty pink PPT manganese sulfide. Manganese sulfide, dirty pink color PPT or buff color PPT. And to this manganese sulfide add dilute HCl and boil so that it dissolves and forms corresponding manganese chloride. MnS is soluble in dilute HCl and forms manganese chloride. To this soluble manganese chloride add sodium hydroxide so that it forms white PPT of MnOH2. White PPT of MnOH2. After some time, we can observe brown PPT of MnO2 dot H2O, hydrated manganese dioxide. Hydrated manganese dioxide. This brown color is because of aerial oxidation of Mn plus 2 of Mn plus 2 of white PPT. So here Mn plus 2 is present. It undergo aerial oxidation and converts into Mn plus 4 and it is a brown color. So this is how we confirm the manganese present in the original salt solution. Confirmatory test for group 4 cation nickel. To the original nickel salt solution, we add group reagent H2S and ammonium hydroxide so that it forms black PPT of nickel sulfide. To dissolve nickel sulfide, we use aqua regia, HNO3 and HCl. Nickel sulfide do not dissolve in HCl itself. So that's why we are using HNO3 and HCl. It is aqua regia. In aqua regia, the sulfide S minus 2 will undergo oxidation, form sulfur, and NO3 minus will be reduced to NO. S minus 2 sulfide will be oxidized to sulfur, NO3 minus will be reduced to NO. And the remaining Na plus 2 combine with the Cl minus and form nickel chloride soluble salt. To this nickel chloride soluble salt, we add dimethyl glyoxime in the presence of ammonia so that it forms nickel complex and the complex color is red color. Complex color is red color. So if you see the structure, so here four nitrogen atoms are connected forming the dative bond, and here you can see 5-member ring, here you can see 5-member ring, and here you can see 6-member ring. It is a hydrogen bonding, and it is a 6-member ring, it is a hydrogen bonding. So the left side is it is a dimethyl glyoxime ring having the negative charge. It is another dimethyl glyoxime, it is also having -1. So simply you can write NiDMG2, NiDMG2. So it is a stable form of complex and it is having the red color. The presence of red color confirms the nickel in the original salt solution. Confirmatory test for group 4 cation cobalt. To the original salt solution, we add group reagent H2S in the presence of ammonium hydroxide so that it forms black PPT of cobalt sulfide. To this black PPT, we add again aqua regia. So cobalt sulfide also not soluble in HCl, so that's why we should add aqua regia. So in this case, sulfide S minus 2 will be oxidized to sulfur and NO3 minus will be reduced to NOCl. NO3 minus will be reduced to NOCl and CO plus 2 form soluble product with Cl minus. So it is a cobalt chloride soluble salt solution. And to this solution, we add potassium nitrite in the presence of acidic medium. In the presence of acidic medium, we add potassium nitrite. Therefore, CO plus 2 combine with NO2 minus, and form yellow PPT of K3CONO2 6. Potassium hexa O nitro potassium hexa O nitro cobaltate 3. It is a yellow PPT. It confirms the presence of cobalt in the original salt solution. Analysis of group 5 cations. Group 5 reagent is ammonium chloride, ammonium hydroxide and ammonium carbonate. Ammonium chloride, ammonium hydroxide and ammonium carbonate. So calcium, strontium, barium, these are the group 5 cations. Once group 4 cations are absent, once group 4 cations are absent, add ammonium chloride, ammonium hydroxide and ammonium carbonate to the original salt solution. If white PPT appears, it indicates the presence of group 5 cations. For example, barium carbonate white PPT, strontium carbonate white PPT, calcium carbonate white PPT. Once white PPT is formed, add dilute acetic acid. That means these PPTs are soluble in dilute acetic acid. These three PPTs soluble in dilute acetic acid. And then divide the solution into three parts. Divide the solution into three parts to confirm the presence of barium, strontium and calcium. First, we have to identify barium and then we have to identify strontium and then calcium. It is an order we have to follow. First barium, next strontium, next calcium. Confirmatory test for group 5 cations. First we test barium. We take the barium salt solution. To the barium salt solution, we add group reagent ammonium hydroxide, ammonium chloride and ammonium carbonate so that we can observe white PPT of barium carbonate. And to this add acetic acid so that barium carbonate is soluble. Barium carbonate is soluble. And to this soluble salt solution, add potassium chromate. Add potassium chromate. If yellow PPT barium chromate is observed, if yellow PPT barium chromate is observed, then we can say the original salt solution has barium. We can also confirm it by considering flame test. To the in flame test, we take the platinum wire. First, initially we heat the platinum wire, and then dip in the conch HCl, and then dip in the barium salt. Barium salt. Again, this platinum wire which was dipped in the barium salt will be heated in non-luminous flame region. In non-luminous flame region. If we observe grassy green color on the flame like this, if we observe grassy green color of the flame, then we can confirm barium salt. Then we can confirm the salt is barium salt. Confirmatory test for group 5 cations. Group 5 reagent ammonium chloride, ammonium hydroxide, ammonium carbonate. And here we confirm the presence of strontium. We take the original salt solution of strontium and to this solution we add ammonium hydroxide, ammonium chloride, ammonium carbonate so that it forms white PPT of strontium carbonate. To this add acetic acid, the strontium carbonate soluble in acetic acid, and to this soluble salt solution add ammonium sulfate. Add ammonium sulfate. White PPT of strontium sulfate will be formed. White PPT of strontium sulfate will be formed. We can do one more confirmation test to confirm the presence of strontium, that is flame test. In the flame test, we take the platinum wire, we heat it in the flame. After that, we dip in the conch HCl and dip in the strontium salt and then again heat in the non-luminous flame region. If we observe crimson red flame like this, if we observe crimson red flame like this, so we can say the original salt solution has strontium. Confirmatory test for group 5 cations. And the group 5 cation reagent ammonium chloride, ammonium hydroxide, ammonium carbonate, and here we test for calcium. We take the original salt solution of calcium and to this we add group reagent ammonium hydroxide, ammonium chloride, ammonium carbonate so that it forms white PPT of calcium carbonate and then we add acetic acid and the white PPT dissolve in acetic acid and to this soluble salt we add corresponding ammonium oxalate. So it forms white PPT of calcium oxalate. Finally, it forms white PPT of calcium oxalate. It confirms the presence of calcium. So we can do one more confirmation test, flame test. In the flame test, we take the platinum wire, we dip in the concave cell, and then we dip in the calcium salt, and then we heat in the non-luminous flame region. If we observe brick red color of the flame, and we can confirm it is a calcium. Suppose if you see this brick red flame through the through the blue glasses, it looks like greenish yellow. It looks like greenish yellow. So like this, we can confirm the presence of calcium in the original salt solution. Analysis of group 6 cation Mg plus 2. Once group 5 is absent, then the solution may contain magnesium carbonate because magnesium carbonate is soluble in the presence of ammonium carbonate because NH4 plus combined with the CO3 minus 2 and this equilibrium will move into forward direction, will be shifted to forward direction so that magnesium carbonate is soluble in the presence of ammonium ions. That's why to confirm the presence of magnesium, so we take the original magnesium salt solution and to the original salt solution we add disodium hydrogen phosphate. Disodium hydrogen phosphate. If we observe white PPT of MgNH4PO4, if we observe white PPT of MgNH4PO4, we can confirm the original salt solution has magnesium. We can confirm the original salt solution has magnesium.